problems here. We'll see an example today for integer problems, but it's a general problem solving paradigm. So approach, right? So last week we saw backtracking, where we had a depth first search, right? And we explored it. We have a dead end. We had to backtrack. So what was the issue? Well, issue was if you reach too many dead ends, right? If you have too wide a space to explore, right? You have too much, right? Maybe let's see if I can draw a paint. Let's see if our smart. I wonder if this works. I don't think it's going to work, right? It's probably not. I don't have to draw it here. I guess use my mouse, right? Yes. Again, my mic turns off. I don't know how it happens. So thank you, Gust. Right. So again, so relaxation, idea of relaxing. Here, not you. Well, you can also relax a little bit, right? But you relax the problem. You relax here. You can relax, but also you relax the problem, right? Meaning you remove some constraints, conditions for the problem. You make the problem easier. You make the problem easier, in effect, right? You don't want to make the problem harder, right? So why would you want to do this? So this is a big idea from today. You want to have idea is to relax the problem so in such a way that you have an easy, right? Easy, or let's call it easier, quicker, right? Algorithmically quicker way of determining a possible solution bounds. So bounds, limits, right? So basically how bad can it be or how good can it be, right? So this is the idea. So let's say you have a easier problem of your original, and you have this sort of cheat code. You determine, okay, you run this easier algorithm, and it tells you, okay, this easy problem will have a solution of 100. I'll just use a scalar, for example, right now. Just solution is 100, right? Well, if you already, and that's the easy problem. So this means your hard problem is not going to be probably 100. It might be much more, right? So, but you already have a solution of 85, right? So this means you can safely get rid of this branch of this solution. So basic idea is you look at this branch, okay, it's over 100 or over 9,000, right? And you get rid of it because you already have a solution for 85, right? So it's sort of, again, so by relaxing, right, so making the problem easier, you gain access to faster solution, right? And if this faster solution is, even that is not good, right? That means you cannot win. You cannot win in this branch. This branch is useless or fathomable, as the slides today will show. There's some terminology used, right? Basic concepts, right? Conquering or fathoming, right? We have best bound and we discard. We get rid of the subset if the bound does not give us optimal solution, right? So again, you can say it's part of divide and conquer approach. Of course, we divide the problem in smaller choices, right? And so some basic ideas here, right? So we discard the subset if the bound says, okay, this is no good, right? So let's look at an example, and this is going to be an example of so-called linear programming, linear optimization, right? I don't know if you have taken any linear optimization courses. Probably not. Anyone? You have some. Okay, a year ago. Okay, right. So, so the idea is this: you can find, you have some constraints in this case, a whole bunch of constraints, and you want to maximize something, right? Here, you want to maximize z, right? A function, we will call it, and we have this formula for this function, x1, x2. These type of problems, you of course usually have not only just two x1, x2, it has multiple dimensions, right? Again, for visual purpose, we are showing you only two variables, right? But in real life, you have maybe 100 or 200 or I don't know, a couple thousand maybe of these variables, right? It's possible, right? So then here we have only two variables, right? When we want to maximize this z, right? Of course, if you had no constraints, put all balls to infinity, right? I mean, it's not really, it's just, infinity. The answer is infinity, right? Easy, right? However, we have constraints. First of all, we have x1, x plus x2 has to be less than 6, right? Right? So, okay, that already puts a severe crimp. So if this was the only constraint, what we would do? We would probably do, well, first of all, we could put x2, right? They have to combine, right? So you put x2 as large as possible, x1 as small as possible, because x1 gives you less gain, 5 times x1, 8 times x2, right? So obviously you want to maximize x2, but that's of course, then the problem's still not really solved. It's like an easy version, not really useful, right? Here, we have the other restriction, 5 times x1 plus 9 times x2 has to be less than or equal to 45, right? So now the thing that's more interesting. And also next thing is, this is actually a double constraint. It's actually two constraints in one. First of all, it says x1, x2 has to be over 0, at least equal to 0 or more. That makes things more interesting again. So we can't use any, cheats of negative infinity and things like that, right? That we kind of, the problem is not really useful. No, but there's another constraint in this particular case. It says the answer has to be an integer, right? And this makes the problem harder, right? Because again, those who remember your linear programming, right? If these answers can be done as floating, in general, right? We can produce solution. There's pretty nice algorithm for solving these linear programming solutions, basically, right? So that's the idea. So the big idea is to relax this problem. So the question, what to relax? Well, we could relax everything. I mean, we have basically 4 constraints here. We could relax all of them. But then again, problem is just, there's not really, doesn't help us much. But the idea is to relax this particular constraint. In this case, in this type of problem, you say, okay, we need an integer solution, but we'll use this idea that we can use it for general solution, right? That we'll use any floating point values. This will give us at least estimate where our answer should be, the area where the answer should be. So that's a big idea. All right, let's see if my mic's still on, right? Hopefully everybody can hear me. Okay, sound is good, all right? Sound okay? Thumbs up if yes, thumbs down if you can't hear me, right? But then of course you wouldn't respond at all, right? So win-win. Okay, so now we can use the L pair. So this is called L pair. In this case, we call linear programming relaxation. So again, relaxation, it can be applied to any type of problem. Again, you might have some sort of easier problem, basically, right? And again, oftentimes, you can think of easier problem, but it might not help you solve the original problem because it's maybe too much of relaxation. You relax too much, right? And you fall asleep, right? So no, that's not good. So, but in this case, right? So we can use this linear programming relaxation here, so we can find this solution, right? But it's not a problem. It's not a solution to our problem because we need an integer, right? But we know. So, but this gives us immediately the cheat code 41.25. We know this is. We cannot do better than this, right? Why? Because if we are allowed to use our floating point values, real values, right? This is the solution we will get, right? And again, we are not going to go today, not going to look at the linear programming way of solving it, right? But there's a couple of ways of doing it. But we usually, you can see one of the things, one of the realizations is if you have this type of problem, right? You have these lines, right? You have the more than, it has to be over 0. You have 1, 2, right? And notice here, you can see this, right? These lines which bound, right? Which give you these sort of, I guess say basically, fence in the solution, basically, right? So from all directions, right? So, but this means is that in general, the solution will be, this is proven by, I think, Richard Hamming, or if I'm not mistaken, no, somebody else, but, or George Danzig, possibly. I think possibly George Danzig, right? That the solution lies on the edges, not necessarily on the, only on the, what you call corners. We'll call them corners, right? Yeah, we'll call them corners, right? But it's possibly also an edge, right? So we don't have to explore the middle, right? So that's from the original, the way of solving. It's not going to be here. However, our problem is slightly harder because our solution is, well, it might be one of these, right? It might be inside. It might be inside. It's probably not, obviously, it's not going to be here, right? We know that in this case, it's visually obvious, right? But it could be one of these, actually. It could be this one, for example, right? We don't know yet. We don't know yet. But we will use these guidelines, right, to provide the way of branching our problem into smaller sub-problems, and then we'll be able to obtain a solution. Okay, so we have this maximum optimal value, but it's an upper, so it's optimal upper bound, basically, right? We cannot do better, right? So again, this assumes we have solved a slightly easier problem, and we have a solution for this slightly easier problem. So we know this is a goal. This is our goals, right? This is our life goals, but we probably not going to reach them, right? Maybe we get lucky. So of course, if these were integers, then that would be the answer, right? But we need to solve branching step. We partition, right? So this is a kind of a slightly tricky. So we partition the feasible regions, basically, right? So let's observe, right, that every feasible point, well, x2, right? X2 should be, well, x2 is this one here, right? Yeah, x2 is here, right? So x2, well, it has to be between 3 and 4, basically. Solutions should be somewhere here, right? So we are going to cut the problem in half, right? Why? Because basically it says 3.75, right? The solution. So it should be, we're going to explore it. We divide our problem into not halves, in 2 branches, right? In 2 branches, and we'll explore both of them separately. We'll use the same. So basically, we say, okay, like in this picture, we have a completely some bad paths, but we branch out into different sub paths, and we'll explore them separately, right? So let's take a look. So what we do is this: we're going to have 2 sub problems now. We're going to say we have this problem where x2 is 4 or more, and x2 is 3 or less, basically, right? So we can find, again, for these separate problems, we can find optimal solution, again, using this linear programming cheat code, right? This algorithm, again, which we don't have to look in here for today's discussion on. We've come up with 2 answers, right? So let's take a look, right? So what do we have right now? Well, we have one gives us 1.8 and 4 and gives you value 41. Okay. Well, it is less than 41.25, right? But can it be a solution? No, because the x1 is 1.8. It's floating, I call them floats. It's a real number, right? Doesn't work. Not applicable to this problem. However, how about this one? 3 and 3. That is 2 integers, 3 and 3. Okay, great. And it's 39, right? It's 39. So can we go home yet? What do you think? Well, we have a solution. If somebody just asks you for any solution, not the best solution, yeah, you say, okay, here's solution. I'll go home. I'm tired, right? But we are not done yet, because what we have done just now, we have solved for this particular branch, right? 3 is the maximum answer, right? We relaxed. We still produced the answer which meets our other constraint. It just so happened in this case, right? But it's less than 41.25, 25, and it's also less than 41, because this is more crucially 41. We have not finished exploring this problem here, right? We have to still do some branching here. We have to explore this problem more. The sub problem has to be divided again into more sub problems. All right, let's do this. So we have our solution 3 again. So this goes back to my little ugly drawing, right? So we have a solution 3. We have for every possible, right? This is actually a maximum solution again with if we were allowed to use the real numbers. Now, and we have a branch, right? We have integer, so we stop here. It's a solution, but right. So there's no need to explore it anymore. We already have a solution here. We have the best possible solution for this sub branch. However, we have to explore this branch more. Maybe let me close the door. So on this screen, no, I don't think it's connected. No, it's not connected. All right, let me continue. So let's see what next. So we are gonna divide this upper part. We could branch again on x2. We could branch on x1, right? It's not necessarily. So we are gonna branch on x1 in this case, right? The new restriction, right? Well, x1, right, has to be less or equal to 1, right? Other restriction, right? We can, because we have integers, right? We had 1.8, so 1 or 2, right? We don't know, there's nothing in between, no integers between 1 and 2, right? So we know that x1 over 2 is infeasible completely. There's no solutions whatsoever, right? It's not allowed, right? So that's completely immediately discarded. We are left with this sub problem, right? This particular sub problem, right? And we have a solution for this sub problem already. We have 1 and 4.44. And what can we do? Is that a solution? Is this a feasible solution? No, because of course it does not meet the second x2 does not meet the restriction, the constraint that it has to be an integer. So you can hopefully now you can see what's our next branch. How are you going to branch this time? We are going to branch on this value. And what's going to be here? What's condition will be for x2? This is x2, right? So what can it be? It can be larger than 4, lesser than 5. Yeah, I mean, no, that's a solution. I mean, if you had 4, but we can only check what we can start looking 4 or less or 5 or more, right? Right. So we have to. In this case, it's easy. We are getting very close to solution, right? Let me draw this, right? We have basically. Can I draw this? And I can't draw. I can't draw. Right. Can I draw? No, I can't. I'm not allowed to draw this here, unfortunately. This is you can do drawing here, right? Draw. Oh yeah, there you go. There you go. Right. So we have this branch, right? And that's where we're going to branch now, right? 4 or less, 5 or more. And of course, here we see there's only 4 and 5 left, right? But in general, that's how we branch, right? Again, if you have multiple variables, you could branch on any which let you do this, basically, right? So here we have this. This is our 3, right? Infeasible. We still have to branch here. We still have to branch, right? So x1 for x2, right? x2 less or equal 4 on x2 more than equal 5, right? So that's what we're going to branch. So let's take a look, right? So in this case, yeah, and we can solve both of them, right? In this case, we are left with integers, right? And we'll get the best solution here because there's no floats. So we are left with 0, 5 and 1, 4. So both are solutions. And 1, 4 has a value of 37. That's less than what we were needed. However, 0, 5 gives us 40. And in this particular case, we have a win, right? So this is going to be the optimal solution for this constrained integer linear programming problem. Now, again, in general, these problems are, so I believe they're NP hard, I believe. Let me double check, but integer ones, right? So meaning they're not completely solved. If you have a very large space, it might not be completely solvable. We can get very good estimates, right? So in this case, it's solved very nicely, right? So this is our solution, right? This is our solution. So in this learning example, we're dropping a lot of branches immediately, right? It's very easy, right? Again, real problems are made harder, right? We have multiple variables, but again, some things to remember that we we're able to branch on the same variable a couple times. Like in this case, x2, we branch on x2 here, right? And we also branch on x2 second time on a sub branch. So we x2, x1, x2, right? This is allowed. This is totally normal. Also, if you think about it, be interesting for you, you want to play around with this particular problem, what would happen if you branched on the first step, you had two floating point answers, right? So theoretically, you could have branched on x1, right? So check 2 or less, or 3 or more, right? That's possible. And then you have slightly different solution 3. You should arrive at the same answer, right? If you go back here, let's go back to original problem. Let's go here, right? This is the original, right? We could have branch, we get this answer. So we can check, all this here, right? And also everything here, right? That'd be an alternative approach, right? We could check these two subspaces and see. What we will get is, right? We get same thing. We get 3, 3 here, right? And we get something here, right? Probably the same 1.8 something, whatever the what was it? 2 and something. No, we get a little bit different answer. We get something 2 something. It will be the maximum again, and then this would let us branch more, right? So maybe slightly longer, but it will be a same approach, right? So hopefully, again, in this case, it's nice and visual, right? We have these steps. Why is branch and bound so relatively hard in general? Because we don't usually have these nice visual steps. We have to think, okay, first of all, need to think of some way of relaxing a problem, right? And there's many ways of making problem easier, right? I mean, okay, no restrictions whatsoever, right? No constraints whatsoever, that's not going to help you, right? So you need to think of relax a little bit and gain with the aim of gaining some sort of like cheat code of getting an easier problem we can solve. We know how to solve. We can solve quickly. That's an important point. In this case, the whole working was predicated on the fact that we know how to solve linear programming problems for real numbers or floating point numbers in a efficient manner, right? Efficient manner, quotes, right? So yeah, so this could be another example, right? You can try this at home, right? So that's the big idea. Let's see some more examples where we can do this. So this was a linear programming problem, right? But there are other instances of problems where we can do it. Do you remember we talked about the greedy algorithm from, I think it was 2 weeks ago, right? The knapsack, right? And you have two ways. Actually, you have multiple knapsack problems or backpack problems, right? We had the integer one, right? And we also had the fractional one. And do you remember the fact that fractional one was easily solvable, right? You get easy solvable, right? It is a greedy approach, right? Greed is nice to have, and it works, right? And it works for fractional knapsack. So if you need to solve you need to solve an integer knapsack, right? Where 0, 1, yes or no, do you put an item in a backpack or not? You could use this fractional to do a branch and bound approach and do these estimates and see, okay, this branch is worth exploring. It's worth putting like that piece of metal or that piece of gold or whatever you are carrying in your backpack or butter or whatever, right, in your backpack. Yeah, that's a good branch to explore, right? It gives you hints, basically, it gives you the branch to explore. So yeah, but in general, this means, of course, you need to come up with some cheat code, basically. And do we have more people joining? No. Okay, no, that's our rector. Okay, sorry. Yeah, all right. Yeah, let's not meet that yet. So let's explore another slides, right? Same approach, right? So again, so we are looking for feasible, right? Again, we're doing depth first, right? We have to explore all the different branches, but the branch and bound can be used to without exhaustive. So exhaustive means brute force. Check everything, right? Check every possible variation, but in general, we don't want to do it, right? Because it is gonna, basically it's just too compute extensive, too expensive, extensive, takes too long, right? Takes too much memory, and so well, DFS you can do it, don't really need memory, but if you're doing like recursive search, but still, yeah. So you need a mechanism to generate branches in general, again, any, right? And a mechanism to generate a bound. So this is my cheat code. So bound is the cheat code, right? You need a way of generating quick solutions, right? So So this will be applicable. If you can't find cheat code, well, too bad, right? Too bad. Well, no. So we'll see this again. So the idea is this: there are lots of so-called NP-hard problems, right? Meaning they are actually need exponential complexity, right? Solve brute force approach, right? I'm very simplifying things a little bit here, but they can be meaning using branch and bound, right? Right, so we can terminate early, right? It's an average. So on average, this is going to be very efficient. So it does not solve you in all cases. You can still generate some really adverse, like evil cases where your branch and bound will keep branching, and you still end up with exponential complexity, right? So that's the worst case scenario. But in average, most problems, which are, yes, theory paper, you read, okay, yeah, traveling salesman, that's a really hard problem, NP hard problem, right? But using these type of strategies, if you want a real life situation, you can solve it, right? Yes, maybe some evil adversary, right? Some demon will get you really come up with a bad problem, right? But on average, you'll be generating a lot of wins. So that's of course is a, we live in the real world, right? So we get actually real solutions, right? So yeah, so this actually would be the shortest path problem. We will talk about shortest path in general next week from Yuka Dijkstra. Let's look at this here, maybe slowly here. Multi-stage graph searching problem, right? So maybe jumping ahead a little bit here, right? On we need to find the shortest path from V0 to V3, right? A greedy approach would be, of course, take one, take shortest, right? And then take shortest, right? Well, you go here, right? You go here, right? And always take the shortest. And it looks like it actually gives you the solution here, right? I'm just looking at this. I have not seen the slides in a while. So if I try to remember, right? So, but yeah, we can see the branching, right? Go one, go three, go two. We can transform our problem, right? In this case, it's a search problem, how to get from V0 to V3 into this sort of like different ways of doing it, right? So we go to 1 1, right? We go to 1 2 1 3. We go 2 1 2 3 2 1 2 2 2 2. So different ways of going, right? Like stages, right? I guess you're not allowed to go back, I guess, in this case, right? Theoretically, right? It's not prohibited, right? It just be very expensive, right? So so this does not cover all the possibilities. If you're allowed to go back or you're allowed to loop, right? It's literally infinite possibilities, right? But here, okay, so this is actually a simpler case, right? And so you have 3 possible early choices, and then each of those have 2 possible choices. So basically 3 times 2. So that's what 3 times, sorry, yeah. So we have 6 different paths, right? And again, in this case, of course, again, brute force, 6, 6 possibilities, right? It's trivial to calculate, right? But right, in general, of course, it will not be so easy. So again, it seems like this is one of those cases where even greedy approach would solve 1 3 1, right? Or 2 2 1, right? Well, the greedy would give you a good solution, optimal 5, right? Because I don't see a shorter solution. This is 2 2 1. Well, possibly, I think these slides have an error, I think, because if you have, because we can think of counterexample. Remember from our greedy search, if this was 1, I think this might be a 1, then we would have then this would be the optimal solution, but it's not a greedy solution, right? So yeah, let's take a look here, right? So we can solve it, right? And yeah, so feasible solution cost 5, right? 5. Yeah, so this is the upper bound. This actually seems like, so I think that this, yeah, they have to fix it. So this is the error. Yeah, there's an error. This actually, I did this. This is my handwriting actually from a long time ago, right? So this 1, right? So the original slides were wrong. This should be 1, right? And then it makes sense. Otherwise, we're not going to get any wins. So we have this. This is our initial solution, right? Upper bound, right? I mean, there's no point of looking at solutions which are worse than this, right? So, so then we can generate some bounds, right? We explore the other paths, and we can already see where the actual possibilities arise, right? So we can see this is actually going to be our solution here, right? Again, so we can discard, if this is like 9, we can of course immediately discard, right? Because it's over 3, right? I mean, it's over 5, but it's over 5, right? So 1 2 3, right? So over 5 would be the solution, right? So yeah, so upper bound, lower bound, and we keep branching on maximization or minimization problems, right? Eventually we reach the solution. So traveling salesman problem, in general, this is considered so-called NP hard, right? This means it's basically exponential as far as we know, right? So we can, so what's who knows traveling salesman problem? Who knows what it is? Anyone? You heard it, right? So what's the goal in traveling salesman? You're a traveling salesman or saleswoman, right? Sales robot, I don't know, sales bot, and you need to have you have gas mileage, you have a gas allowance, right? Or you have some budget, and you have a whole bunch of cities to visit, so they're connected. You have costs, gas or mileage or whatever cost you want to be, and you want to me, yeah, or time, exactly. And you want to minimize this time or money or something, you want to minimize something, right? So in general, so what would be the greedy approach? You start, let's say, in Riga, you have to visit all Latvian cities. You go to Jurmala, why? Yeah, it's like if you assuming, I'm gonna pretend like, I don't know, like Babite or I don't know what's the name, Baluoji, that does not exist, right? But I think what's Marupe is a city now officially, right? Right? They gained one of the they gained like Adaji gained city status, and I think Marup also gained city status. But let's assume Jurmala is the city and it's the closest. So that'll be the greedy approach, right? Go to the closest. It's very tempting, and you always go to the closest, right? It seems very tempting. This should be like, wouldn't this give you the best solution? Well, it will give you a solution, right? Just one solution. It will give you a solution, but not necessarily the optimal one. Because why do you think, okay, why? Because it's possible if you think about it. Let me give you a counter example. I'll do my paint example. Paint example here. So I'm go here, right? And I'm going here, right? And then I go here, right? And I go here, right? And I go here, right? And here, this simple example. This is Riga. Let's say this is Riga, right? And let's say, assume I'm going to, this is Uagre or something, this is Daugava maybe, right? Okay, so if let's say this city, whichever it would be like Salaspils or Ikšķile, I don't know, right, it would be closest, but this is a little bit slightly like maybe a little bit more. Let's say Jurmala is a little bit more, right? Let's say Jurmala, right? Jurmala, right? So what happens? This is a really simple example to show you that greed does not work in this case, right? So we end up in Daugavpils here, right? This is Daugavpils here somewhere, right? Daugavpils, right? So what is the issue? We end up in Daugavpils, like we go through across all Daugava, all the cities in Daugava, like Uagre or something, right? Uagre, right? Right. And we go to Ikšķile, I don't know, Ikšķile or something, right? Let's say, okay. So, and we went through here, right? Right. We end up here, right? All over here, right? So the issue is we forgot about Jurmala, right? So, and this that's where the greed would fail, because we can obviously see here in this case, the solution would be in probably go to Jurmala first and then go to Ikšķile or Uagre, wherever, right? So on across. So because now we have to go back from Daugavpils to Jurmala, right? Again, of course, the question might be, there might be restrictions. Do you want to end up in the same city, right? That's another, of course, city. There's different versions of this problem, right? Do you want to make a loop or cycle, right? Do you want to end up original city, right? That also might be an issue here as well, right? If you want to end up in original city, this makes things harder, of course, right? Well, you go back to Riga directly, you take a flight from Daugavpils to Riga. I don't know, there are no flights, not yet, right? No. So, and then you go to Jurmala, right? And then you're going, but then you have to go back to you. So again, so you can see the greed, it will give you a solution, but it will not give you the optimal solution, right? Right. So, all right, just give you an idea. But there are ways of using some techniques, and this is where I'm not going to explain you directly. This is going to take too long time. We could transform this to matrix, right? These would be cities, right? Right, and we could generate some possibilities, right? And it's a relatively advanced idea. Again, if somebody who wants to do a thesis or something, it's a very wide topic still, right? So split the solution space, right, and predict a lower bound. Again, same thing, right? So maybe upper bound, lower bound, right? And if your lower bound is, the worst case, right, exceeds the upper bound, this means you don't take this. It's a bad direction. bad branch, basically, right? You split, same approach, right? So here, of course, this involves matrix, so it's not as easy to see here. So I'm not going to go into this here, right? Again, so all solutions, right? When you have, so but this we can make it visualized, right? This we can generate. So you have all solutions, lower bound 96, right? So and we can see all lower bound 96 with this possibility of this move, right? And maybe there is without arc, it's 128, right? So so basically we take, of course, the one where we have the where it's feasible, right? So now so that's the splitting, but I'm not going to go into this here right now because it's mostly matrix, right? But the same idea which we explored you in our linear programming or previous slides, same approach like we used here, same type of decision tree. Again, it all reduces to a decision tree. Underneath, you make decisions. So if you have a problem which involves decisions, right, you need to find a solution. You got to make multiple decisions. Then branch and bone would be applicable. Okay, I have also some notebooks I can show you. It's going to be probably very short. Let me see here if on GitHub. Yeah, and there's some theory if you want to read. Also, there's a Geeks and Geeks link. But I also have a collab from IBM actually with some libraries solving linear programming. They're pretty nice. Let me see if I have them here in my code space. Fantastic meme. Let's see if it works. Let me see if I have it here. I don't think I have it here. Parsing, branch and bound. Oh, I do have something here. Okay, let's see what I have here. Yeah, this actually shows you how to solve using the traveling salesman, right, actually. But again, the code here would not be really that fun. Let's see, I have NACPAC maybe. Let's see, not very, you can explore this notebook, but I want to see something else. Greedy. I don't see it here actually. Right, so we could of course try to do a knapsack with this approach again. Do we have anything else interesting? Yeah, linear programming. Let's see. Yeah, this actually is. Yeah, this has the notebook. I'm not going to actually run it. I'm going to show you what it shows you. Right? So linear expression again. You already taken some linear programming, so this goes into basics, right? On why it's useful. Of course, there's a solver. Again, in this case, it's not applicable too much to our topic, but well, it gives you a library, so you can solve the problems immediately, right? You can model them, right? A lot of real life problems can be modeled on, this linearity. Basically, you have to produce. The example is given. You have to make. You're running a factory. You have to make desktop phones and cell phones, right? Kind of unrealistic. Maybe 10 years ago it was realistic. Who makes desktop phones these days? I don't know. Well, I was thinking, okay, I guess you could say network phones like those, Cisco phones, like the ones they use in offices, I guess, right? But for example, I was trying to find a real desktop phone like it use normal old phone jack. You can't find it because I threw it away like 5 years ago, right? And you probably don't have. Does anyone have one? Does anyone have a grandma or grandpa who have it still? Is it still possible to have it? Like a real actual phone. You have it? Where? Your grandma. Yes. Is it, the question now is it a network? Is it a internet phone, or is it actual copper? It's a real phone. Oh, cool. Okay. Okay. That's even amazing. There is a rotary dial. That's actually even more amazing, right? When it works, actually. Oh, okay, so you can make a call. Okay, super. Okay. So yeah, so that's the thing, of course. So this, it's still possible. So I think the constraint should be different. Desktop phones, you make much less desktop phones, more cell phones, right? But the idea was this: that there is production facilities which are shared, right? And you can model this type of problem, right? Optimization problems, right? You have a painting time, assembly time, right? I don't know, the factory could be in China, I don't know where, right? And basically, you want to maximize what? Well, depends, maybe profit, maybe maximum amount of phones, right, produced. Again, you can only make, you need to make at least 100. Maybe there's like a, you know, preset limit, right? When you have these constraints, and you guess you want to minimize the time possibly, right? So, no, maximize the revenue, right? Yes. And getting paid $20, I don't know, euros or whatever for cell phone, only $12 for desk phone. I mean, this is a really silly example, right? But yeah, but this is basically a linear programming example, right? You have some constraints and you want to get the answer, right? Again, a lot of things can be modeled like this. And also thing is, if you think about it, there's sometimes you have these binary, you know, flags like, should you know, I don't know, should you work on Saturday or should you wear a red hat or something like that? I don't know, like Boolean flags basically, right? Well, you can actually model them as 0 1s also in these linear programming examples. Actually, sometimes you can use that as well, right? We can transform Booleans, right? So let me show you this. Yeah, so this same approach, and maybe see if you can show this. Yeah, I can show you the picture. Yeah, let me show you this here. Yeah, so yeah, so same thing basically, same thing which I just showed you before half an hour ago, right? But except you have a real life problem, right? Also a kind of, you know, and again, the solution will be somewhere here on one of these edges, or maybe one of these where we meet, right? On somewhere here, right? Lower bounds, again, notice again, in this case, it's not 0, it's actually 100 and 100, right? So these lower bounds are sort of like limit here, right? You cannot, there's no solutions here because these lower constraints. And again, in this example, right, again, it can be easily solved by library, of course, right, the algorithm, right, or linear programming. But again, right, its solution is going to be somewhere here, basically somewhere here, right, and we will find it. But basically, yeah, eventually, right, you get a solution. So I think here in this particular notebook does not have it, does not have the branch and bound in this particular case, right? You can read it anyways, but beyond, yeah, beyond is going to be the one we want, right? So branch and bound, right? Branch and bound, branch and bound, branch and bound. Yeah, I think it has one. Yeah, we'll have it here. Okay, yeah. So same approach, same idea again, that we have a non-integer optimum right here. That's a solution, but we are not allowed to make 299.8 desktop phones, right? That 0.8 is not good. Same goes for 851.93 cell phone. Of course, you could argue, I guess, in real life, if it's like a month-by-month base, right, you can still keep working, right? Just make those, and then, you know, it sort of rolls over, maybe, you know, and then round up at the end of the year, right? Again, it depends. Again, seems like, again, we are very close to the solution, but again, we can see that it's the actual solution is, this is the optimal solution if you allow the non-integer values, but the real solution will be here, and we are going to be branching based on this. Yeah, so that's what we're going to be doing, right? Let's take a look how we do it again. So same thing, right? We solve it. In this case, we have x, y, z. We have 3 variables, right? And we have fractional approach, right? On so we know that's the upper bound, right? And basically we keep going. Lower bound is minus infinity, you know. But right, so we solve it. So we branch on x either 1 or less, right? Because we branch by first one, or x is 2 or more, right? We find solutions, same approach, except we have 3 variables, right? Same approach. Oh, come on here, right? So, and we get an objective, and again, we see this is not solution, right? 1, 0, 5.2 is not solution, right? Here we get 2, 0, 4, and now we know this is the actual solution, 10, right? Because with these variables, that's a solution, and we know we have something. We have something already. Upper bound was about 1.11, but we still have to explore this side, right? 11.4, right? We still have to explore it. So we'll do that. Right? And let me go down a little bit, right? So we don't have to. We don't know it's best. 2, 0, x is 2, y is 0, z is 4, right? So 10 is currently the best, but not the best, but it's a current best, right? And we keep exploring. So we check, okay, Z cannot be over 6, not possible, infeasible. So we explore this branch. And what we have here, again, 11 and 1/3, right? So 11.33333. And we have what? X is 1, Z is 5, and we have 1.3 for Y. So what are we going to do? We're going to branch on Y and explore either Y 0 or less. So in this case, only 0 on or Y 1 or more, right? So let's see what happens next. Yeah, and I see, right. On here we have two solutions, 1, 0, 5. Okay, and that's 11. It gives you objective result 11, right? And this is 11.2, right? 1, 1, 4.6, right? So we will have to explore this, right? Why? Because we have not yet searched this one particular, right? So we have to branch on this one. I think we'll get infeasible, I believe. Let's double check. So we.
At this point, the objective where you have to search further would be like something lower, like 10. Would it be okay to stop at that 11?
Okay, so you mean where we have 10 here?
No, if we have 11 there, but on the other side we have 10.
Okay, well, yeah. Thing is, we should not be able to. Okay, the thing is, if this is 11, right? But thing is, we should not. Then this should not be. So but this is 10, right? If this is 11.
No, it's the one that's currently infeasible.
Okay.
IP3.
IP3, yeah, here, right? We could stop, right? We could. Where here, right? So here, right? If you get 10 here.
No, sorry,
IP5. This one here, right? If you get 11 or 10.
If you get lower, yeah.
Yeah, if you get lower, we stop.
Yeah.
Then if you get like 10.9, we stop. 10.999, stop, because we have 11 here already, right? So only reason we have to keep exploring IP5 is because it's slightly more than the current best, right? We stop. We completely, what's the word? Phase them. I'll call discard, or basically purge, right? We get rid of it when we see it's not, it doesn't give us any improvement, right? So here we still have to make, technically, we have to make a step, check if there's anything good here, right? We branch on this 4.6, so explore Z being 4 or less, or Z being 5 or more. So we'll finish in moments. So 1 second, right? So, and I think it's, so basically we get 9. This is better, right? So here, what's the interesting moment is it's actually technically more or 5 or more, basically. Sorry, could be equal. So in this case, this has two solutions: 105 and 015. And if you look at the formula, there's an obvious reason for that. Let's check out the formula, right? Let's check out the formula in this case, right? This formula was where's the formula? Let me find it. You can find the formula now. But basically, yeah, this one formula, you see, x plus y plus 2z, right? That's what we're trying to maximize, right? So in this case, x and y, they're equal weights, right? They give you to the solution. If one of them is 1 or the other one is 1, right? Same weight, right? So that explains why the solution is. So of course, it depends on these constraints. You could come up with different constraints, and which would not let you use x or y. It would be 0 basically, right? In this case, there are two solutions, two integer solutions. Again, right? So we had the 3 constraints, 3 non-negative integer values. Again, there are libraries like this IBM library. It's a public open library from IBM. It's been maintained for maybe not maintained for a few years, right? Meaning whoever was being paid at IBM is, I don't know, they don't work on this project anymore, but it's open source. You can download it and use it if you want to check it out more. So same thing again. Another thing is you can, of course, model many other things. You can model like a specific constraints of some machine, like Boolean machine. If machine 1 is used or assembly machine 2 is used, right? It's possible to do things like that to add extra constraints, of course. All right. So that is basically the basics of branch and bound approach. And again, it applies even if your problem does not benefit. You don't have this huge decision tree. Always think about whether you can relax your problem into something slightly easier. Not too easy, but a little bit easier. And then we can use something existing to solve this easier problem to give you estimates. So next week we'll work on graph algorithms and shortest path problems. We'll see this in some of the following lectures, this idea again of relaxing a problem, of making it easier, of doing some things easier, right, to achieve our more complex goal, basically. All right, and that's it for today. So do the quiz, again, do the quiz for the today's quiz, branch and bound. And again, you can, there's also a paper, there's interesting discussion with one of the creators of this technique. Why does it work at all, right? Again, you can follow it. It's, I think, on ACM. Let's see if this is still alive. Yeah, this guy here, right, about discussion, right, now optimization, right? There's discussion. If you want it, this is not required. Next week, we start looking at graph algorithms, especially we'll start with one of the most famous one, Dijkstra's shortest path algorithm. All right, thank you, everyone. All right, I'll see you next week. And I'll stop the recording. You're welcome to ask also questions in Latvian now. Let me see here.